All right, so why don't we get started? Last time on Hurwitz's theory, what we did is we spelled out the algorithm for tropical Hurwitz number coming from the definition of tropical Hurwitz number as the degree of a tropical branch morphism. And we saw that this is a cute little algorithm that expresses Hurwitz numbers as weighted sum over a certain type of graphs, but it's not just cute. It just allows us to witness some properties of double Hurwitz numbers, namely, piecewise polynomiality and wall crossings. Okay? So there is sometimes an advantage into reproving something which is already known in a different way, because that might give you like a tool for going farther in understanding of the subject. And then we did I presented the first proof of the correspondence theorem between tropical Hurwitz number and algebraic Hurwitz numbers. And this was a representation, like a symmetric group theoretic proof, because basically it said, look, thanks to the kite and joint equations, which is basically telling us how the cycle type of a permutation in the symmetric group can change when you multiply by a simple transposition, thanks to the kite and joint equation, we can basically see that these monodromy graphs are an indexing set for the count of monodromy representations, right? Where each monodromy graph basically tells you what the cycle type is of every consecutive product of a product with a transposition. Okay? And so then, of course, there's some little details to be checked, but it so happens that the multiplicity that the kite and joint equation gives you is exactly the same as the multiplicity that Hannah computes with these big matrices, and so we're in business and we win. What I want to do today is I want to, again, stick in the realm of understanding and motivating why the correspondence theorem works, but from a geometric perspective. Okay? And so we're going to degenerate, right? And so here is my picture, right? So this is very much following what the philosophy that Francesca was presenting yesterday in her talk, right? So if you're trying to count something which is geometrically sophisticated, now what you might want to try to do is break it up into simpler pieces and trade some of the geometric complexity with combinatorial complexity, right? So a philosophical lesson in math is that you hardly ever win, right? It's not like there's a magic thing that all of a sudden all of this complexity of this problem disappears, right? But oftentimes what you can do is you can move the complexity from one place in math to another place in math and hope that where you move it, then you have more tools or different tools or tools that allow you to solve the problem. And so again, there is a very simple picture that should at least give an idea of why it should be possible to use this technique in this situation. And this picture is purely topological, right? So suppose that I have a particular cover that I'm counting in some particular Hurwitz problem, right? So here it is. I have my branch points down here. I have my surface up here. And I have a monodromy representation. And what I've done here is I've just sort of highlighted that I can take a loop around the branch point and I can lift it, right? And this lift gives me a permutation associated to this element in the fundamental group. In this case, the permutation is 2, 3, 4, 5, right? Is 2 disjoint transposition, right, in S5, right? And then what you can do is you can say, okay, you call your topology friend, right? Your topology friends are going to cast a lasso, like the kind of things that we don't know how to do in algebraic geometry, but they're perfectly fine. Like cast a lasso on here, look at inverse images, and then pull that lasso tight, right? And then as you do that, right, what's going to happen is that eventually, when the length of the loop of this lasso becomes 0, you've created some kind of singularity here, right? So you have a nodal curve here, but, as you pull this lasso tight, you're going to also pull this ones upstairs, right? And so you're also going to create singularity here, right? And so what you see is that now what used to be one cover of a given degree d of just one sphere has become a cover from a nodal curve to a nodal rational curve. And then you can look at them one at a time and you can say, okay, well, this is going to be some Hurwitz cover for some other Hurwitz problem, and this is going to be some cover for some other Hurwitz problem, right? And so, at a first very qualitative instance, you might be like, cool, I can express my Hurwitz number here somehow in terms of products of other Hurwitz numbers, where the degree remains the same, but the genus, for example, decreases and the number of branch point decreases. Okay? And this qualitative intuition is right, but then you have to make it into something a little bit more precise, right? And the first thing that you notice is that, okay, so as you tighten this green loop, right, you certainly separate the branch points. Some of them end up on one side, some of them end up on the other side, right? But this green point, this node itself, right? If I look above it, I don't see 5 inverse images. I see only 3, right? And so this thing has itself become a branch point, right? And so the Hurwitz problems that we need to consider in this approach, right, is have the original branch point split, but then one new possible branch point here, right, that we're going to track, right? So let me say that, okay, I'm going to have ramification profile eta over this new point. Okay, in this case, eta is 2, 2, 1, right? Because I see that I have 2 sheets coming together here, 2 sheets coming together here, and just 1 here. Okay, so then let me try to build quantitatively the degeneration formula. So I guess what I'm saying is I want to write my original Hurwitz number, Hg eta 1, let me say eta r, mu 1, mu s, and the reason I'm calling the branch points with 2 different letters, I'm secretly thinking, okay, I'm going to call etas the ones that are going to fall on the left-hand side of the green loop, and mu the ones that end up on the other side of the green loop, right? And I'm going to first write down as a sum of products of Hurwitz numbers such that the ramification profile over the green point is eta, and I'm going to sum over all possible etas. Right? Again, this is just, in a sense, almost an empty statement, right? Because all I'm saying is like, start with all possible covers, right? So that you have all your elements that count your Hurwitz numbers. Pull all the lassos. As you pull the lassos in these degenerate pictures, you're going to see different ramification profiles over this node. Separate the covers by the type of ramification profile they have. Okay? Great, because now, well, let's try to understand, for a fixed eta, right? What is the number? Let's consider the covers, the set of covers that degenerate to such a way that this gives profile. Sorry, for fixed. I said eta, but it's no. It's no. Okay, and I claim that I have a map from H G1 eta 1 dot 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 eta R nu Cartesian, or yeah. Well, let me, sorry, these are numbers, but let me call, or set AG1, the set of covers, right? So I have a map for the Cartesian product. Okay. I'd like to build a map and say, okay, this map is a bijection, and so this component is the product of these two Hurwitz numbers, and so my total Hurwitz number is the sum of this product of two Hurwitz numbers over all the etas. But I have a couple subtleties that I have to address. Okay, so the first subtlety is that if you start from an element of this set, you're basically saying start from looking at this picture on the left and this picture on the right, glue them together and tell me which picture here came from. Okay? And there's one problem here, which is that even if you give me a picture on the left and a picture on the right, and I glue them together, to like go in there, put my finger in this hole and open it up, I need to know if I'm coming in. So here I have no problem, right? I come in here, I open the hole, I gotta come out here. But here, I come in here, I need to know when I open the hole if I come out here or I come out here. And same here. Right? And so just having a pair of covers does not allow me to uniquely recover this thing. So I have to decorate, right? Say that for each one of these parts on the left, I have to mark one of these segments, right? And once I mark one, all the others are determined, because remember that locally analytically the map around here looks like z goes to z to the k, so I know what it means to multiply by root of unity. Right? So once I know that this arrow continues to this arrow, I mean, in this case, I only have 2, so obviously the other one is determined. Even if I had 27, I would multiply by 27 roots of unity to get a cyclic order of the arrows on one side and on the other, and then I know how to match everything else. Right? So this means that if I want to define a map, I need to multiply, right, by a set of ways to mark one of the blue ends coming out of each green point. Okay, again, this is maybe not the most mathematical way to say it, but I hope it's one of the most intuitive.
So may I ask, so
yeah.
the thing is that this point in the modular space of covers is the intersection of lots of components, and the set of ways is telling me what are all of the components of the boundary where this point lies?
No. I'll come back to this question, but it's a stacky nonsense business. It's not a because this is really about each individual point here, right? So if I had the full ramification here, so I have only one inverse image, then what you see is just a divisor, but I still have a factor of d, right? It's a cyclic order. So this is something that in the, Abramovich, when they did this orbital, they called them the ghost automorphisms, right? And already when you call something a ghost automorphism, it means that there is something that you don't understand very well, right? But I mean, I think people that love stacks understand it very well now. I'm going to say a few words later. But right now, I mean, this is just sort of like, really sort of, there's no moduli here, right? All the branch points are fixed. There's only topology, right? And so now I have a map here, okay? But in fact, I don't quite, I mean, this map is not a bijection, but if I want to make it into a bijection, because what happens, right, if you give me a cover here and a cover here, these covers come with labeling of these green points, right? Because this is our definition of Hurwitz numbers. Every inverse image is labeled. And that is good because that's telling you what to glue with what. Right? The point label 1 on the left, point number 1 with ramification order 2, you're going to glue it with the point label 1 with ramification order 2 on the right, where this is right and this is left, but other than that. Right? And so on and so forth. Right? So the fact that these covers have a labeling of these points tells you know how to glue them. You actually know how, in only one way, from two pictures like this, get a picture like this. But after you've done the gluing, you're still remembering a labeling of these points. Are you still remembering that this is the point with ramification order 2 that you marked by A? And this one you mark by B, and so on and so forth. And this information that you don't have here, because once you open the loop, these are not points that you track anymore. Right? So really, let me call set about eta, right? What really this gives is a bijection between this set and the set of covers that they generate times a marking of this partition 2, 2, 1.
No.
Huh? Sorry, and I keep saying eta, and every time I say eta, this should be no. Thank you. Okay? Now, again, now don't take my word, right? Get yourself a carafe of your favorite drink, which I know for the Kentuckian is bourbon, right? And sit in a dark room with your carafe of bourbon until you're convinced that this actually is true and it makes sense, right? But if you do that, right, then you have these bijections, so the number of elements this set is the same as this set, and so what you really want to count here is this. So you take the cardinality of this set divided by this, right? And so what pops out, this is the summation over all etas of the product of the eta i's over automorphisms of eta, and then for just to be able to squeeze into the space that I have left, let me say h1 times h2, but we know what we mean. h1 is the Hurwitz number of where you have all the etas on one side and the nu, and h2 is you have the nu and all the mu's on that side, right? And the g1 And the G2s are determined by the Riemann-Hurwitz problem. Okay? And there is something that I'm very happily shoving under the rug, which is connected versus disconnected, but let me not get into it because it would be a technical tangent that does not really make anything more enlightening. Yes?
Pretty sure you're talking about that.
Yeah, no, that's why we're here for 2 weeks.
Like, what about the new getting double counted? Like, how's that? It doesn't both sides, I guess. Or, I don't know.
Yeah, so nu is not really getting double counted. The thing is that, you know, nu, I mean, this is what we call like the kissing condition, right? So whatever ramification, when you, in order to be able to stick two covers together and being able to like put your little pinky in here and open these things into loops, right? You need to make sure that the ramification profile on this side and on this side match, right? So really this is saying that there's only one point here. It's a nodal point. Over this node, in a little open neighborhood, you have two branches here and a bunch of pairs of branches above, and the ramification on each side has to match. Yeah. Cool, absolutely. Yeah.
So on that note, so H1 and H2, are we considering on either side everything except nu because we've already accounted for it, or is it in fact part of H1 and a part
Yeah. So let me write down just what H1 is. So hopefully I'm good. So this is the Hurwitz number corresponding to some genus G1. It is going to be determined by the Riemann-Hurwitz formula with, and let me say R equals 0, right? All the ramification I'm actually, you know, putting it in red. I'm not doing anything simpler. And then I'm going to put all the etas and the nu is H1. So it's the Hurwitz problem that I see on this side, including obviously the nu. And H2 will be the Hurwitz problem that I see on the other side. Yeah, thanks for asking. Yeah?
Does G1 and G2 change?
Yes, it will. Will. Ask Riemann-Hurwitz.
Do we sum over all possible G1?
We sum over all possible G1 and G2 that add up to G. But again, this will not be something free. The G1s and G2 will be determined by the Riemann-Hurwitz formula. And the only issue whether and they're always going to add up to G. The only issue is that connected versus disconnected, but let's not talk about it. I mean, I'd be happy to talk about it, but if, again, I would like to talk about something else in this hour. Yeah?
So, to me it seems that you're taking that pointer and you're taking the image and then you're counting the image with the taking care of automorphism and also reduceness.
Yeah.
Okay, now, but it seems to me that you're ignoring reduceness, right?
Oh, yes, I'm totally ignoring reduceness.
Why?
Because I want to. No, I mean, I'm joking, but I mean, this is not, has nothing to do with any sophisticated intersection theory or moduli space problem. This is a count of covers. This is topological. This is ramified covers, right? So I don't even know as a topologist doesn't even care about reduceness, right? So I don't have to worry about it. In a second, when I'll say, okay, now let me parallel this to a problem, you know, of intersection theory and some moduli spaces in algebraic geometry, that's something to worry about. And that gets thinking, you know, and somehow like, this is somewhat related to what Francesca was asking, right? But it's about proving that this branch map is flat, and then you count these inverse images, and you know, yeah. But I mean, you're right. There's a if you want to think of this as an intersection theoretic problem, there's sophistication that we're not seeing right now. But if all you want to do is Hurwitz numbers, you can actually remain at this level. It doesn't matter. Yeah.
Yeah. So don't you also need the thing coming in as you need the thing coming out?
No, because the thing coming in, it's sort of like, I mean, you know, this is like a principal mu d bundle, right? So you really, I mean, you really get to choose one however you want to be your principal, your first one, right? It doesn't matter, you know, I really need to know which of these to connect to which of these. So you can choose one here however you want and say, well, which one do I connect here? Right? If you had said, well, but my favorite one of these two is this one, right? Then, well, when you connect this one to this one, you get the same gluing that I get from connecting this blue one to this blue one. Right? So we're counting the same thing. Right? So on one side, the labeling comes for free in the sense that it doesn't matter. It's a way to sort of band the gerb.
After choosing on one side.
Yeah. So on one side, you can choose it freely, right? Because it doesn't cost anything. But on the other side, you can't choose freely because you really need to know the one special one that you've chosen to write, how does it continue? Yeah. Those are great questions. Cool. All right, so let me again step up the sophistication a little bit right now because actually before we step up the sophistication, let me write two things. Thing one, right, is that this is a degeneration formula for splitting a genus 0 curve into two genus 0 curves and separating part of the branch points. There's also a degeneration formula where if you have a higher genus base, you can cast your green loop around a non-trivial element of the first homology. And by doing so, you're going to get a degeneration formula that reduces the genus of the base by 1. Right? There is also, and it's on the notes, and it goes very similarly, a base genus reducing degeneration formula. It works very similarly. Okay? And then thing two is that a consequence of the degeneration formulas, both the splitting the base points on a genus 0 component and being able to reduce the genus, but a consequence is that any Hurwitz number can be computed from base genus 0, three branch pointed Hurwitz numbers. Right? In the sense that if you want to know some Hurwitz number of a curve, that corresponds to base curves of genus 2, right? First shrimp this loop, and the degeneration formula tells you how to reduce this to a bunch of Hurwitz numbers where the base genus curve is 1. Then you shrink another loop, and that reduces the genus by 1 again, and now it's a bunch of Hurwitz numbers where the base curve has genus 0, and then start separating branch points so that now all the Hurwitz numbers are in terms of like smaller number of branch points until you get to 3. Once you get to 3 branch points, the game doesn't work anymore because no matter how you cast your green lasso, you're always going to have 3 points on one side. Right? So this you can degenerate further, right? And in fact, this is essentially going to be, it's not even like, oh, so maybe this is an interesting expression that relates three-pointed Hurwitz number. No, it isn't. there's really only one thing here that contributes, it's in kind of a trivial way, and it's really this is equal to this, where this green point has the same branch as this. So it's not that interesting, okay? And again, for somebody that thinks of Hurwitz numbers as the theory of the representation theory of the symmetric group, this statement is nothing by saying that the class algebra, multiplication in the class algebra of the symmetric group is determined by sort of multiplying sort of two things and getting a third one. So it's a binary operator, right? It has two inputs and one output. But whatever, right? We're not representation theory, so ignore that. Okay, so geometrically, now let's take a side step.
Can I ask you a quick question?
Yeah.
So about this relation between between Hurwitz numbers. So when we did the double Hurwitz calculation, we did it by this chain degeneration. But I could also do that same double Hurwitz calculation by a non-chain degeneration. So do I then get interesting?
Yeah. In fact, given how late I get in every lecture, probably, but that's kind of what I wanted to conclude. But that's exactly you get some interesting relation, and the other way is like the Bertrand-Bugalimi-Calkin sort of algorithm, right? Okay, so ignore what Drew said, because I'll come back to it. But
Just the last comment.
just the last, yeah. I mean, you can also ignore all the 5 lectures, but then why are you here, right? And of course, the answer is like, because I got a free vacation in Moraga for 2 weeks. Again. All right, so geometrically, right? So let's, again, come back for a second to the double Hurwitz number realm, so I can paint the geometric picture that matches our algorithm, and then I'll generalize it if I have time at the end of the time. But remember that we have this space of relative stable maps that Francesca convinced us to love yesterday, right? Let me call it M, G, P1, eta 1, 0, eta 2, infinity, bar, and I'm going to stop here, right? Or maybe like, let me put some rubber here, right? And this space generically has an open dense set that parameterizes cover of P1, where over 0 and infinity, I'm prescribing the ramification profile by eta 1 and eta 2. And everywhere else, well, again, generically, I'm going to have a certain number of simple transpositions. With separate branch points. Right? So this contains the Hurwitz space inside, but then there's some boundary components. This comes stratified into smaller and smaller strata, and the boundary component will correspond to covers of a nodal rational curves, where this nodal rational curve is not some arbitrary rational curve, but it's just a chain of P1s, a bunch of spheres attached one to the other, such that there's a point that I'm going to call 0 prime on the first component, another point that I call infinity prime on the other component. Okay. And I'm going to enforce the kissing condition over every node. I'm going to enforce the ramification type over 0 prime and infinity prime. And I say nothing else other than I need to have genus G. So in particular, the kind of bad behavior that I could have is I could have points of non-simple ramification over some of these points. And I can either have a contracting component over some other points. Okay? And so again, knowing nothing about this space other than the fact that it's stratified like this will give me some idea of, sort of some things I can do with this space. In particular, that, this is the same as the Hurwitz space, and so there's certainly like a natural branch morphism here that takes a picture like this and ignores the cover and just records the positions of the red and the blue points. Okay, and now it's a non-trivial theorem of Fantecchi and Pandaripande, essentially, that this branch morphism actually extends over this whole compactified thing. And it's, in the appropriate virtual sense, it's a virtually flat morphism. Okay? And so somehow, I'm cheating because I'm not really, I'm cheating Alessio in the sense that he asked me a question and I'm essentially answering by saying, well, the answer is really in a paper of your advisor. I'm not really going to tell you much about it, right? But again, I trust your advisor, so right? So we have this branch morphism to this, and let me be careful here. This is going to be an m bar 0, 2 plus r times epsilon space. Well, what do I mean? This is one of these heavy, light, weighted spaces where I have 2 points, namely the points that I'm going to send to 0 and infinity. They're heavy. Nobody messes with them. And our points, which are tiny and light and go wee, right? And they do all sort of crazy things. But if they want to come together and party, we let them. Okay? So this is also called a Losev-Manin space. Okay? And if I were to be fully honest, I would actually take a quotient by SR because my R light points are really not marked. I cannot distinguish them. But again, these are all details, right? And the key point, and it's proven that this thing is well defined and virtually flat. Which tells me, in particular, that the degree of this branch morphism I can compute so the degree of Burr, I can compute it as the push forward to the class of a point of the pullback of the class of a point. This is a very fancy and confusing way that you can use at cocktail parties if you can impress people to say count a finite number of points. Right? You take a point in the target space, look at its inverse image, it's a finite number of points. How do you count them? You push forward to the class to a point. Right? That sounds very stylish. Right? Might not impress your 7-year-old cousin, right? But beyond that. Okay. Sorry?
Your 7-year-old cousin should not be at the cocktail party.
Like Francesca and all the times be, why not? I remember my cocktail party at 7. They were a lot of fun. Okay. Anyway, right? So, what is the next Yes, Vance.
If you don't want to worry about quotienting by SR on the bottom, can you label your points upstairs? There, then with the space upstairs.
So let me think about it for a second. I think you can. I mean, the thing that I worry about is what happens when these points crash, but I don't think you really worry too much, right? Because okay, points blah and blah and blah and blah now are all mapping to the same point. Yeah, so I think you can.
It's true tautologically, right? Because the quotient has a cover.
Yeah. 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 There you go. Cool. All right, so if you see something like this, right, you should keep in mind what Dhruv would tell you. So let me draw Dhruv, right? Oh, sorry, this is better. Dhruv would tell you not all points are equal. Okay, so don't choose a random point to do this computation. Choose a special point, right? And what is a special point? Again, you know, I was about to write something and then I realized that that came out as kind of like dirty, so let me just say, very deep. And if this already sounds a little dirty, like whatever I was writing before was even worse. So, but what I mean is like, all right, this is why it's good to like organize things with friends and not with random people. This was not planned to come out like this. But anyway, so there's a stratification, and so we're going to choose a point in our moduli space of targets that corresponds to a chain which is as long as possible. Okay? So what does as long as possible mean? Well, remember that you cannot degenerate this P1 forever because you have a stability condition. Every component must have enough points on it to have weight at greater than 2. Right? And so the longest that you can degenerate is in such a way that you have, of course, you must have your 0 and infinity that are points of weight 1 on the ends. Now notice that before I mark anything else, every component has already weight exactly 2, right? Because each node also has weight 1. So this is almost stable. And it becomes stable so long as each component has at least something else. Right? And so the most spread out I can do is each component has exactly 1 of the light points. Okay? And now what we have to do is we have to look at what is Burr inverse of a point. So what are all possible pictures of this type that I can draw over this target, knowing that I'm allowed sort of arbitrary ramification over each component over 2 points, and a simple transposition kind of ramification over a third point. Okay? But, so what kind of covers? Appear in Burr up a star of this particular point. Okay? So It's a good exercise that I don't know if I probably forgot to put in the notes, but let me say it here. So from the Riemann-Hurwitz formula, plus cut and join. What's the situation, right? If you have a Hurwitz problem where you have 2 points, eta 1 and eta 2, and only one single transposition of our third point, and nothing else, right? Then the cut and join equation tells you that the cycle type of eta 1 and eta 2 cannot be too different. Right? You either join a cycle or split a cycle, right? But the length of eta 1 and eta 2 must differ by 1 exactly. Right? Then you can see, like, what is the Riemann-Hurwitz formula telling me? And the Riemann-Hurwitz formula will tell me that the genus of this cover is pretty darn negative. And in fact, it's so negative that the only possibility that I have is that the cover that I have over here is a bunch of trivial genus 0 component. And by trivial, I mean it ramifies only over 0 and infinity with the same order of ramification. So they're of the form w equals z to the k. Ramifies to order k over 0 and infinity. Except for one component, which is a genus 0 curve with one fully ramified point on one side and two ramification points on the other. So all the kind of things that you see over here must be all of this type. Okay, a bunch of what are called trivial covers and one non-trivial cover, but barely non-trivial. Still genus 0, right, with only 3 special points. Okay? So I guess the exercise is to prove this, right? So above implies that above each irreducible component of the target, you see something like this. Okay? And again, because over each component of this target, you see something which is a bunch of trivial covers, but at most one of these trivalent things. I mean, what you see is a bunch of, like I said, these are 0-dimensional strata on the space of covers. So all you have to do is count them. And here's where, where Alessio's question becomes very relevant, because it's not just counting them. Each of the stratum is not actually a reduced point, so you have to actually compute the multiplicity with which you count it. Okay? So now I'm gonna, let me see. I'm gonna just make a quick nod to where to find the answer geometrically. Like I said, originally this thing was called, well, you have to count with ghost automorphisms. But, let me say, so locally near a boundary stratum, or let me even say boundary divisor. Oh, wait, I mean, locally, a boundary divisor in a space of relative stable maps is not a product of spaces of relative stable maps. Okay, so why am I telling you what it's not? Right? It was because that you might think that that's what it is, right? So a boundary divisor in a space of relative stable maps will correspond to when the target splits in two, right? And then I just told you, like, okay, now I have a special point here and a special point here, and I've made, I'm enforcing the Kissick condition. So I have a special point here, and then I have my V points that V however they want on either side, right? And so why can't, and I have a map here that satisfies the Kissick condition. So why can't I just sort of pull these two things apart and say, really, to specify a picture like this, I need to give a pair of relatively stable maps, and then just glue them. It seems like it should be the case, right? And in set land, it is the case, right? But in stack land, it's not. Because, and again, I mean, even in set land, it's kind of like we saw with the picture that I erased, right? There's some delicate things to figure out, right? I mean, you can't just glue at random, right? You have to make some choices. And the way that this is manifested at sort of this more geometric, sophisticated level is that instead of a product of spaces of relatively stable maps, it is actually, it's a fiber product over, and now I'm going to say a bunch of words that either you already know them and you're going to be very happy, or if you don't know them, feel free to completely ignore them, right? The inertia stack of the stack quotient point over SD. Okay? So, what I'm saying is that there's a sophisticated way to think about all this additional data that I need to make the gluing happen in terms of this weird creature saying, okay, I have some evaluation morphism, and I killed my green. No. I have some evaluation morphism to some geometric monster called a stack. In fact, a lazy one because it has inertia. And saying that I can glue to things means that this evaluation of these green points to this thing inertia stack must match. Whatever. If this motivates you to study stacks, great, right? Otherwise, move on thinking like, thank goodness somebody worked this out for us, right? And the only intuition I possibly can give in a few minutes is that, really you should think of this as a fraction of a point. And you would like to say, well, this stack is 1 over d factorial of a point, right? Because it's 1 point, but it has an automorphism group over the d factorial. The inertia components of these things are other stacks there, and they're not quite 1 over d factorial points, but 1 over something of a point, some fractions of a point as well. And fiber products need to preserve degrees. And so when you fiber product over something which is fractional, you actually get some multiplicity, right? And this is exactly how these multiplicities happen, okay? And again, I'm sure, but I'm not the right person to ask, that you can very carefully interpret this multiplicity also as saying like, well, if you just look scheme theoretically, there's some no-reduced structure in these points that is captured by this statement. But I'm definitely not the right person to go into details with that. But okay. So all of this to say that, okay, when you're counting these boundary points that you looked at above this particular degenerate stratum of the space of targets, you have to be a little bit careful and count them with the appropriate multiplicities. And these multiplicities are exactly what becomes the weights, the product of internal edges in the tropical counts, right? So let me just make this a little bit more precise. A second. So let me draw one of these covers. Here's, for example, one of these covers, right? And the multiplicity with which you have to count this cover because of this stacky business is essentially the product of the ramification orders at each of these attaching points. Okay? But then what hopefully it becomes sort of pretty evident is that if I draw a picture like this, you can certainly associate to it a tropical cover. There it is. And the multiplicities, the ramification order of these points can become exactly the weight of the edges. And because maps from genus zero curves to genus, maps from any Riemann surface to a genus zero curve has a well-defined degree, right? So the number of zeros, the number of poles must agree, then the balancing condition must hold. Okay? And finally, the way that we've counted this graph was by the product of these edge weights. And so we have a perfect matching, right? We have a bijection on the sets of the object that we're counting, but we're counting this object with weights, but the weights are the same, and that's why the correspondence theorem holds from a geometric perspective. Okay? Questions? Comments? Okay, so in the last 2 minutes, the second half of the lecture is that this is not really special to just double Hurwitz numbers, right? If you have Hurwitz numbers with arbitrary branching conditions, and even arbitrary base genus. Okay, so I may be interested in a Hurwitz number of genus 1 with 3 branch points, right, that are very deep. Eta 1, eta 2, eta 3, and I'm using deep in 2 ways, so they're very ramified. Right? I can take sort of a decomposition of this picture in such a, so for example, let me draw. So 1, 2, 3. 1, 2, 3. No, that doesn't work. Let me do this here. This is a loop. And am I done? 1, 2. Yes, then I'm done, right? If I pull these 2 loops, what do I get? I get one of these, one of these, and one of these. I have eta 1, eta 2, eta 3, 2 components. And I can think of this as a zero-dimensional boundary stratum in an appropriate moduli space of targets. Then in this case, I need to set up a little bit differently. I would do the admissible covering compactification. This becomes n bar 0 n. That's great. I look at the inverse images. And these inverse images will be, again, things that over each component look like this. But then it might glue in some weird and funky way. So this one might glue to this one, and this one might glue to this one, and so on and so forth, right? I don't know, right? And then I could, for each one of this picture, draw a corresponding tropical curve and get a tropical kind of correspondence theorem, a tropical Hurwitz numbers and a tropical correspondence theorem. The one enormous difference with the simple Hurwitz, with the double Hurwitz number case, right, is that these kind of Hurwitz numbers I'm looking at, they must allow for 3 special branching points. Okay, because even if I start with something which, where some of these are transpositions, so I say, well, I don't have 3 special branching points. But the way of degeneration is that now I have no control over these 3 green points. Okay. And so this tropical algorithm, this tropical general Hurwitz numbers, will need, as a geometric input data, something that tropical geometry does not see: triple Hurwitz numbers. So these graphs will be counted with a vertex multiplicity, which has to come from geometry. Right? And so this is, again, one can think of it of a bug or a feature of tropical geometry, but tropical geometry, it doesn't see everything in algebraic geometry. It sees certain things, right? And setting up a correspondence theorem in tropical geometry often also entails understanding the limits of what tropical geometry can see and saying what is instead the input that has to come from geometry. And then, the success of tropical geometry is whether the geometric input is actually something like reasonable. Right? And then from this reasonable stuff, what does tropical geometry allow you to reconstruct? Okay, so of course I had planned to spend more time than these last 3 minutes on this, so I'd be happy to chat more tomorrow afternoon or something, and maybe I'll say a little bit more in the last lecture, but I don't know because there's something else I want to tell you in the last lecture. So let me stop here.